Hello, everybody. Uh, my name is Alex, and I am your Math 6B CLAS tutor. And today I wanted to go over some limits practice. The reason we want to practice some limits is because, well, in order to determine whether a sequence converges, you have to be able to do a limit. So here is a bunch of limit problems. So they range from, in the beginning, relatively easy limits, to, at the end, some hard limits. And then hopefully in the course of doing these, we'll be able to extract some more general results here that will allow us to do more limits. Okay, so I'll start off with a nice easy one. Number one, limit as n approaches infinity of the natural log of n. Well, I suppose to do this, well, you just really need to just know how the log function behaves, and the log can get arbitrarily large. So the limit of log of n is infinity, or natural log of n, ln of n, whatever. All right, so why is that? So we can do, I'll show you a little engineering proof of this. My background's engineering, so this is not a proper math proof, but it can be converted into a proper mathematical proof. Roughly speaking, well, if you believe that e raised to the infinity is infinity, then if you take the natural log of both sides, then that would also mean that infinity is the same thing as the natural log of infinity. All right, so that's limit number one. Limit number two, this one's going to require a little bit more work. Natural log of n divided by n. So for limit number two, we want to do, what's the limit as n approaches infinity of natural log of n over n? Well, let's see here. So at first, so we just showed before that the natural log of n approaches infinity, and then also n approaches infinity. So this gives us infinity over infinity. Well, what is this? Well, this isn't 1, because infinity isn't a number. It could be 1, it could be 0, it could be infinity, it could be 5. We don't know. This is an indeterminate form, and so if you remember, one of the things you can do with this is if you have 0 divided by 0, or infinity, so if your limit gives 0 divided by 0, or infinity divided by infinity, then you can use L'Hopital's rule. You have a broken limit, and you can take it to the hospital. Use L'Hopital's rule. And if you remember, the way that works is, well, you just take the derivative of the top, take the derivative of the bottom, try again. So then the limit as n approaches infinity of log n, or natural log n, over n, that would be the same thing as the limit as n approaches infinity of the derivative of natural log of n, which is 1 over n, divided by the derivative of n, which is just 1. And you can see pretty clearly, well, 1 over n goes to 0, 1 goes to 1, so this goes to 0. A general result we can extract out of this is that logs grow slower than polynomials. Okay, so we'll put this as a result back up here. This limit, log n over n, goes to 0. And as a sort of general result, if we have a logs over polynomials, those will approach 0. And if we have a polynomial divided by a log, that would go to infinity. Okay. All right, limit number 3. Limit as n approaches infinity of -1 to the n. All right, how do we work that one out? I'll scroll down here. So 3, limit as n approaches infinity of -1 to the n. So this one is a little bit tricky. We can't really do continuous function stuff with this because -1 to the n doesn't map well to continuous functions. What we can do is just take a look at the sequence of -1 to the n. So let's look at the sequence. Curly brackets, -1 to the n, as n goes from, say, 1 to infinity. And the first few terms of that, so -1 to the 1, that's -1. -1 squared, that's +1. -1 to the 3, that's -1. -1 to the 4, that's +1, and so on and so on and so on. And you can see the behavior of this. It's negative if n is an odd number, it's -1 if n is an odd number, and +1 if n is an even number. So the idea behind a limit is, well, the limit exists if the numbers in the sequence are getting closer and closer and closer to a single number. We say the words one limit that exists. So in this case, there's not one limit. I guess you could sort of say there's two limits, but we just say that a limit doesn't exist. So this does not approach a single number. So we can say the limit as n approaches infinity of -1 to the n just doesn't exist. Or equivalently, we could say the sequence, curly brackets, -1 to the n, diverges. Diverges really just means doesn't converge, right? It doesn't approach a number as you go further and further down the list. Okay, so let's scroll back up, and then we could say just this limit does not exist, DNE. All right, we're making some progress here. Limit number 4. So 2 to the n over n to the 10th. So again, I will scroll down here. Number 4, what is the limit as n approaches infinity of 2 to the n divided by n to the 10th? Well, again, just like with the second limit, we have this infinity divided by infinity, because 2 to the infinity, that's infinity. Infinity raised to the 10th, that's infinity. And so we can, in principle, use L'Hopital's rule. More broadly speaking, if we were to classify the types of functions that we're dividing here, then this would be an exponential divided by a polynomial. And basically, what we're going to determine here is which thing grows faster, an exponential or a polynomial. There's a lot of talk these days about exponential growth. I won't reveal what that is about. I think you guys probably already know. All right, so here, in order to use L'Hopital's rule, we need to know what's the derivative of 2 to the n. So question, what is the derivative of 2 to the n? Well, it's an exponential function. If we wanted to, we could rewrite it with e as the base, where it would be e to the something times n. You might remember, I won't go through the full derivation of this, but turns out that the derivative of 2 to the n, so 2 to the n prime, is just the same thing times natural log of 2. Natural log of 2 times 2 to the n. And it doesn't really matter for our purposes that the constant that it gets multiplied by is natural log of 2, but this is just a general property of all exponential functions. If you take the derivative, you get a constant times the same thing. Okay. Now, as far as end of the 10th goes, well, if we keep taking derivatives, 10 derivatives basically, we'll eventually get down to a constant. The first derivative would be 10 n to the 9th. The second derivative would be 10 times 9 times n to the 8th. And if we keep getting down to the 10th derivative, well, it would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 times n to the 0. So, all right. So it looks like we're going to have to use L'Hopital's rule 10 times here. So, no big deal. Limit as n approaches infinity of 2 to the n over n to the 10th equals, so if we, actually, let me do green here, la hospitalize, 10 times, then we're going to end up with the limit as n approaches infinity. So 10 derivatives of 2 to the n, well, one derivative, well, every time I take a derivative, I just get the same thing times natural log of 2. So if I do that 10 times, I'll get natural log of 2 raised to the 10th. No, not natural log of 10. Natural log of 2, oops, raised to the 10th times 2 to the n. So it's still some constant times 2 to the n. 10 derivatives of n to the 10th gives us 10 factorial, right? 10 times 9 times 2 times, 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is, we can write that as a shorthand, 10 factorial. So the point is that that's just a number, and we're just doing the limit of a number times 2 to the n, which, well, 2 to the n approaches infinity, so that's infinity. And a sort of broader result here is that exponentials grow faster than polynomials. And so you can use that in the future. You say, oh, I got an exponential divided by a polynomial. That's going to go to infinity. All right, so this one is infinity. So that sequence would diverge, I suppose. And we can say that exp over poly in general is going to approach infinity. Or if we flipped it around, poly over exp would approach 0. All right, what about number 5 here? So number 5, we've got 5 to the n divided by n factorial. So let's do that here. So 5. We want to know what's the limit as n approaches infinity of 5 to the n over n factorial. So what do we get when we do this? What happened here? All right, a thing happened. Okay. So this one, we also, like a couple of the other limits, we also get infinity over infinity. So in principle, we could use L'Hopital's rule. But, well, there's a technical problem with that, is what's the derivative of n factorial? That's not a thing that we know how to do a derivative of. The derivative is not even something that's well defined for that, because n factorial is only defined for integer values of n. It's not defined for like a half or anything like that, right? So it's not a continuous function. So we got to use some other way of doing this. And so there's a trick where we could just expand this. So we could say, if n is bigger than 5, then we could say 5 to the n over n factorial is the same thing as 5 times 5 times 5 times 5 times 5. How many 5s is that? 1, 2, 3, 4, 5, 6. I'll do 2 more at the end. So that would be, so there are n 5s right here on the numerator, and on the denominator would be n factorial. So 1 times 2 times 3 times 4 times 5 times 6 times dot, 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 and then the last two would be times n minus 1 times n. Okay, so we can view these as a product of a bunch of fractions. So we got 5 over 1, 5 over 2, 5 over 3, 5 over 4, 5 over 5, 5 over 6, dot, 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 5 over n minus 1, 5 over n. Okay, now here's what we're going to do with this. We're going to group these together. So I'm going to group all of the ones, all of these little fractions here that are 1 or bigger together. And so that's some number. So this is like 5 to the 5 over 5 factorial. All right, I'm going to take a second chunk here, everything except this very last factor. And I'm just going to note that we're multiplying together a bunch of numbers that are smaller than 1. 5 over 6 is smaller than 1. The next one would be 5 over 7. 5 over n minus 1 is smaller than 1. So this is smaller than 1. And then the 5 over n, we're just going to sort of leave alone. And so what we can conclude here is that for any n bigger than 5, that 5 to the n over n factorial is smaller than 5 to the 5 over 5 factorial, and then times 1, because 1 is bigger than this middle chunk here, and then times 5 over n. Okay. Now, by the way, on the other side, we could say that 5 to the n over n factorial is definitely bigger than 0. So we're squeezing this in between two things that hopefully both, certainly the left one approaches 0, hopefully the right one approaches 0. So that's our little trick here. And so now we could say, well, this inequality would be true in the limit as n approaches infinity, right? Because it's true for all n. So the limit as n approaches infinity of 0, that's less than the limit as n approaches infinity of 5 to the n over n factorial. And then that's less than the limit as n approaches infinity of 5 to the 5. I don't know why I can't draw 5 in that exponent there. 5 to the 5 over 5 factorial times 5 over n. Okay. Okay, now this right-hand limit, obviously the left-hand limit goes to 0. This right-hand limit also goes to 0. It's like some number divided by n. That goes to 0. So we get the value of the limit we wanted to know originally is somewhere between 0 and 0. Well, the only thing between 0 and 0 is 0, so our limit equals 0. So therefore, the limit as n approaches infinity of 5 to the n over n factorial is 0. And more broadly speaking, we can conclude from this that factorials grow faster, even faster than exponentials. So factorials grow faster than exponentials. You can imagine this argument would be the same if I had like 123 to the n divided by n factorial. It would be the same thing. It's just the chunk in front would be bigger. So let's see here. So if we go back up there to the problems, 5 to the n over n factorial, that approaches 0. And in general, we can say that exp over factorial that approaches 0. So because factorials in general grow faster than exponentials. These are little rules of thumb that you can keep in mind. Next one, very complicated one. Well, it looks complicated, but it's actually not too bad. The biggest thing you have to remember is that log of n grows slower than n, which we proved over here. And all we have to look at are those guys. So this is basically, for large n, it's 2n squared over, and now the largest thing on the bottom is square root of 9n to the fourth, which is 3n squared. I don't know why my screen keeps doing this, which is 2/3. So for large, so whenever you have a fraction, the only things you have to consider are fastest growing thing on the top and the fastest growing thing on the bottom, and then you have to divide them. There you go. So that's that limit. One more limit to go, and this one's a doozy, but this is a famous one. And after we do this, this is a limit that is worth remembering. So let's clear some space for that down here. What is the limit? So this is 7. So 7. So what is the limit as n approaches infinity of 1 plus x over n raised to the n? Okay, and then hopefully in the future you can remember this one. That depends on your professor's preferences. Okay, this is a large, well, we'll get to this in a minute. So the thing that's tricky about this one is well, first of all, there's an x here, but as far as we're concerned, x is just some number. It might as well be a 5 or a pi or a square root of 7 or whatever, right? It's just some number. N is the thing that's approaching infinity. Okay. And so if we let n approach infinity, the stuff inside the parentheses approaches 1, right? Because it's 1 plus some number divided by infinity. But then the exponent approaches infinity. And so this is an indeterminate form. And what the clever trick is anytime you have an indeterminate form, you can sort of rearrange it until it's a fraction. So in order to do this limit, it's probably best to just give it a name. So we'll call this limit L. L is whatever we get for this limit. So limit as n approaches infinity of 1 plus x over n raised to the n. Okay, and I'll annotate what I'm doing here. So our first step here is, well, the big annoying thing about this is n and the x. Our variable n is in both the base and the exponent. So we want to get this n up here out of the exponent. So get the n out of the exponent, n out of the exponent. And how do we do that? Well, best way to do it is with a log. Okay, so we just take the natural log of both sides. And the only reason for preferring the natural log over log base 10 or something like that is, well, natural log calculus as well. So, it's easy to do a derivative of natural log. So it's n times the natural log of 1 plus x over n, right? Because remember, if we do, right, that's the exponent rule for logs, right? You could bring the n, if it was up at the top there, out front. Now it's a little bit more clear what's going on. This is infinity in front times the natural log of 1, which is 0. And on the one hand, infinity times anything is infinity. And on the other hand, 0 times anything is 0. So what happens if I try to multiply infinity times 0? I don't know. Well, that's indeterminate. So if we want to use L'Hopital's rule, we have to rewrite this as a fraction. So rewrite as a fraction. So we can use L'Hopital's rule. right? Because that only works if you have a fraction, 0 divided by 0 or infinity divided by infinity. And the clever trick to do that is to take that n that's out front and write it as, so I'll leave the log stuff the same, dividing it by 1 over n. So right, multiplying by n is the same thing as dividing by 1 over n. So this is the same thing as the previous line here. Okay, so now we can use L'Hopital's rule. All right, so the natural log of our limit would be the limit as n approaches infinity. So a derivative of the top, and be very careful here. When we do the derivative of the top, n is the variable and x is a constant. So if we take the derivative of the natural log of a bunch of stuff, this would be 1 over that bunch of stuff times the derivative of that bunch of stuff. So derivative of 1 is 0, and the derivative of x over n with respect to n would be negative x over n squared, right? Because it's like n to the negative 1, so you get negative n to the negative 2, and then the x is a constant multiple. Okay, and then 1 over n, if we do the derivative, that's minus 1 over n squared. Okay, right, because it's n to the negative 1. Oh, cool. So these things cancel. That cancels with that and leaves an x. And so we get the natural log of our original limit is equal to the limit as n approaches infinity of x over 1 plus x over n. And then hopefully it's clear this denominator as n approaches infinity just goes to 1, right? Because 1 plus 0. And so we're left with x for the natural log of our limit. So this isn't our original limit. This is the natural log of our limit. So if we undo the log by, what's the verb? E-ing it, exponentiating it, I guess, then L, the value of the original limit, would be e to the x. So our result here is therefore the limit as n approaches infinity of 1 plus x over n raised to the n is equal to e to the x. And this is true for any value of x you may care to plug in. So 1 plus 1 over n raised to the n would approach e to the 1. 1 plus 7 over n would approach, raised to the n would approach e to the 7. 1 minus 1 over n would approach e to the minus 1. All right, so cool. So this is a famous limit, and in fact, in most places, this limit is considered to be a definition. This is a definition of the function e to the x. Okay, so we have some limit practice. If you'd like, I'm going to save this sheet as a PDF and I'm going to post it on the GachoSpace page. And hopefully I will see you guys next time. So enjoy and see you then.